Find your seats. Thank you for coming. Good evening. Welcome to the Bold Ideas in Physics lecture. I am Professor Parker from the School of Physics. I have the pleasure tonight of introducing John Preskill, who will be giving our lecture. The Bold Ideas in Physics lecture is in honor of Professor David Finkelstein, who was a beloved professor in the School of Physics here. Dr. Finkelstein worked on a number of issues, I think, that are related to what you'll hear about tonight in terms of the quantum structure of space-time and actually some early work in black holes and quantum computation and material of that nature. So our speaker will also be talking about similar topics, is the Richard Feynman Professor of Physics at the California Institute of Technology. I would say a well-named institution. So John Preskill has a number of important awards to his name. I just glanced briefly at the very long list, and I will say it's bookended by the following. He was the valedictorian of his high school, and he is also the Bold Ideas in Physics lecturer at the Georgia Institute of Technology, which is already up on his CV, so he's very timely. He's also, by the way, an APS fellow and a member of the National Academy of Sciences. He's done work in quantum information, although he started on cosmology and quantum gravity. He got his first degree at Princeton University and then went to Harvard, where he was a professor briefly before moving finally to Caltech, where in addition to being the Richard P. Feynman Professor, he's also the director for the Institute for Quantum Information and Materials. So without further ado, I'd like to introduce John Preskill.
Thank you very much, Colin. David Finkelstein was a very remarkable physicist. This picture was from around 1958, about the time that he was the first to articulate clearly what happens to you if you foolishly fall into a black hole. What happens is that you can't possibly escape, and you are drawn unavoidably to the dreaded singularity, where you are torn to pieces by unimaginably strong gravitational forces. It isn't pretty, but it was brilliant. And this is just one of David Finkelstein's bold ideas and a career filled with them, so I'm honored to be giving this lecture named after him. And my topic is going to be bringing together two ideas that David Finkelstein was very interested in: quantum physics and information. We have information technology today, which we think is very impressive, but we all know that these will be replaced in the future by new technologies that we can't hope to imagine today. It's interesting, just the same, to speculate about future information technology. I may not be the ideal person to engage in that type of speculation. I'm not an engineer, I'm a theoretical physicist, and I can't claim to be deeply knowledgeable about how computers really work. But as a physicist, I do know that the crowning intellectual achievement of the 20th century was the development of quantum theory. And it's natural to wonder how the development of quantum theory in the 20th century will impact future information technology. Now, quantum theory is a rather old subject by now, but some of the important ways in which quantum and classical systems differ from one another, we've only begun to appreciate relatively recently. And many of those differences have to do with the properties of information carried by physical systems. To a physicist, information is something that can be encoded and stored in the state of some physical system, like the pages of a book. But fundamentally, all physical systems are really quantum systems governed by the rules of quantum physics. So information is something that we can encode and store in a quantum state. And information carried by quantum systems has some notoriously counterintuitive properties. That's why we like to speak about the weirdness of quantum theory. And physicists relish that weirdness, but we're also coming to ask more seriously these days whether we can put the weirdness to work. Can we exploit the unusual properties of quantum information to perform tasks that wouldn't be possible if this were a less weird classical world? And that desire to put the weirdness to work has driven the emergence of a new field, what we call quantum information science, which derives much of its intellectual vitality from three central ideas: quantum entanglement, quantum computation, and quantum error correction. And the goal of this talk is to explain those ideas. But let's start at the beginning. You all know that any amount of ordinary information, what I'll call classical information, can be expressed in terms of indivisible units, bits of information. Or you might think of a bit as an object, like a ball, which could be either one of two colors, let's say red or green. Now, you can store a bit inside a box. And then later on, when you open the box again, the color ball that you put in comes out again. So you can recover a bit and read it. Now, by quantum information, I mean information carried by a quantum system. And it too can be expressed in terms of indivisible units of quantum information, what we call quantum bits or qubits. And for many purposes, it's convenient and appropriate to envision a qubit as an object stored inside a box, but where now we can open the box through either one of two possible doors, with those doors representing two complementary ways that we can prepare or observe the state of our qubit. And you can put information into a qubit through either door number 1 or door number 2, and then later, when you open the same door again, the color that you put in comes out again, just as though the information were classical. But if you put information in door number 1, for example, and then later on you open door number 2, then what comes out of the box is completely unpredictable. It's just a random color. So to read the quantum information, you have to do it the right way. If you do it the wrong way, opening the wrong door, you'll unavoidably damage the information. And we can appreciate one consequence of that if we think about copying quantum information. What would it mean if I had a quantum copy machine? It would mean I could put information into door number 1 of the qubit and then make a copy. And then when I open door number 1 on the original and the duplicate, the color ball that I put in would come out of both of the boxes. And likewise, I could put information into door number 2 of the qubit and make a copy. And then if I open door number 2 of the original and the duplicate, the color I put in would come out of both boxes. But in fact, no such quantum copy machine is possible. We can't make high-fidelity copies of unknown quantum states. And the reason why not is that in order to make the copy, we have to probe inside the box. And if the copier guesses right and uses the same door that I used, then it can copy the information without any problem, just as though it were classical. But if it guesses wrong and opens the wrong door, it will irrevocably damage the information, and there won't be any way to build a high-fidelity copy. So while we might be able to clone a sheep, we can't clone a qubit. Now, as you've seen, I like to think of qubits in kind of an abstract way. But a qubit is always realized physically in some particular way, and there are many possible ways in which it could be realized, and I'll mention a few others later on. But just so you have something concrete to think about, we can imagine that the qubit is carried by a photon, a single particle of light, and that photon has an electric field which could be oscillating either horizontally or vertical, corresponding to the two possible states, the red and the green state that we might see when we look through door number 1. But I could also consider the electric field tilted along these 45-degree axes, and those correspond to the two possible states I could see if I look through door number 2. So if I prepare this horizontally polarized photon with its electric field going horizontally, and then I observe it along these tilted axes, I would just generate a random bit. Now, the really interesting ways in which quantum information differs from classical information, we can appreciate only when we have more than one qubit. So let's suppose we have 2, And they could be far apart from one another. Say one in my lab at Caltech in Pasadena, and the other in the custody of my friend at the Andromeda Galaxy. And some time ago, these particular two qubits were both on Earth, and they interacted in some way as to establish a correlation between them with some unusual properties. Namely, in this particular state of the two qubits, I can open my box through either door number 1 or door number 2, and either way, what I find is just a random bit. Could be either red or green with equal probability. And the same is true for my friend in Andromeda. He can open either door number 1 or door number 2 and just sees a random color, which could be either red or green. So neither one of us, by opening his qubit in Pasadena or Andromeda, acquires any information about what's inside the boxes. We just generate a random bit. And that's peculiar because with two qubits, we should be able to store 2 bits of information. But where is that information hidden? The answer in this case, for this particular state of the two qubits, is that all the information is encoded in how the qubit in Pasadena is correlated with the qubit in Andromeda. Because if I open door number 1, I might see a red or green ball, but if I see green, and my friend also opens door number 1, we're guaranteed to see the same color. If I see green, my friend sees green. And likewise, if I see red through door number 1, so will my friend if he opens door number 1. And furthermore, if I open door number 2 and my friend opens door number 2, we always see the same color. Could be red or could be green, but it's always guaranteed to be the same. Now, there are actually 4 perfectly distinguishable ways in which a qubit in Pasadena could be correlated with a qubit in Andromeda. We could see either the same color or opposite colors when we both look through door number 1 or we both look through door number 2. And by choosing one of those 4 ways, we've encoded 2 bits of information in the 2 boxes. But what's unusual is that information is inaccessible locally. I can't acquire the information by opening the box in Pasadena, or nor can my friend opening the box in Andromeda. It's all encoded in the correlations. And that property of quantum information, that it can be shared non-locally between 2 distantly separated objects, is what we call quantum entanglement. And it's the really important way in which quantum information is different from ordinary classical information. Now, correlations themselves are not very unusual. We encounter them all the time in daily life. My socks are normally the same color, so if you look at my left foot and see a green sock, then you know already without looking that there's a green sock on my other foot. And you might say it's rather similar with the boxes. If I want to know what my friend is going to see when he opens door number 1 in Andromeda, I can open door number 1 in Pasadena to find out. And if, on the other hand, I want to know what my friend will see when he opens door number 2 in Andromeda, I can open door number 2 in Pasadena to find out. So aren't the boxes just like the sockses? Well, I insist no, that the boxes are completely different than the sockses. And the essence of the difference is that there's just one way to look at a sock. But because we have these 2 complementary ways of opening the box, of observing the qubit, correlations among qubits are richer and more interesting than correlations among ordinary bits. This idea of quantum entanglement was first explicitly discussed in a famous paper by Einstein and collaborators over 80 years ago. And to Einstein, quantum entanglement was so unsettling as to indicate that something is missing from our current understanding of the quantum description of nature. And that paper elicited some interesting responses, including a particularly thoughtful one from Schrödinger. The way Schrödinger put it is, the best possible knowledge of a whole does not necessarily include the best possible knowledge of its parts. What Schrödinger meant by that is that even if we know exactly how those 2 boxes, one in Pasadena and one in Andromeda, were prepared, and we know everything about what's inside the boxes that the laws of physics will allow us to know, still we're powerless to predict what I'll find in Pasadena when I open my box, or my friend will find when he opens his box in Andromeda. And it was Schrödinger who suggested the word entanglement for these unusual correlations. And he also said it is rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy in spite of his having no access to it. What Schrödinger meant is it seems very strange that although these two qubits are many light years apart, one in Pasadena, the other in Andromeda, nevertheless, it's up to me to decide whether I will open door number 1 of my box and then know what my friend will see were he to open door number 1, or I can open door number 2 and then I'll know what my friend would see if he opened door number 2. But Schrödinger understood that though these correlations are different from ordinary classical correlations, they do not allow instantaneous communication between Earth and Andromeda, because when my friend opens his box, he just sees a random bit. And that doesn't give him any information about any action I might have taken on my box in Pasadena. Now, this idea of quantum entanglement did not advance very much for the following 30 years, until the work of John Bell in the mid-1960s. And beginning with Bell, we started to think about entanglement in a different way, not just as something very strange, but as something potentially useful, a resource that we might exploit to do useful things. We needn't go into the details, but what Bell described is a kind of game that two parties can play. The two players, Alice and Bob, are on the same side. They're trying to help each other win. And the way the game works is that Alice and Bob receive inputs, and the object of the game is for them to produce outputs that are correlated in some way that depends on the inputs that they receive. But under the rules of the game, Alice and Bob are not allowed to communicate with one another between when they receive the inputs and when they produce the outputs. They are allowed to make use of correlated pairs of bits that might have been distributed to them before the game began. And for this particular version of the game, if Alice and Bob play the best possible strategy, they can win the game with a probability of success of 75% if we average uniformly over the inputs that they could receive. But there's also a quantum version of the game. And in the quantum game, the rules are exactly the same, except that now Alice and Bob are allowed to make use of entangled pairs of qubits that might have been distributed to them before the game began. And by taking advantage of that shared entanglement, they can play a better quantum strategy and win the game with a higher probability of success, about 85% instead of 75%. So they can use the entanglement as a resource to do something, winning the game with probability above 75%, that wouldn't be possible if they didn't have quantum entanglement. And experimental physicists have been playing this game for decades now and winning with a higher probability of success, which Bell pointed out the rules of quantum physics allow. So these super strong correlations really seem to be part of nature's design. Einstein derided quantum entanglement. He called it spooky action at a distance, which sounds even more derisive when you say it in German. But it doesn't really matter what Einstein thought. Nature is the way experiments reveal her to be, and we should learn to love her as she is. So boxes are not like Soxes. With quantum entanglement, you can win a game with a higher probability of success, 85% instead of 75%. Is that really such a big deal? Yeah, it's actually a really big deal. And we can begin to appreciate why it's a big deal if we think about quantum systems with many parts. Imagine it's a book which is 100 pages long. And if that were an ordinary book, written in bits, every time I read another one of the 100 pages, I would acquire another 1% of the information that's written in the book. And after I've observed all of the pages one by one, I know everything that's in the book. But suppose instead it's a quantum book, written in qubits, with the pages very highly entangled with one another. Well, then if I look at a single page, I just see random gibberish. And if I look at all the 100 pages one by one, the amount of information I've acquired is almost useless for distinguishing one highly entangled book from another. And that's because in the quantum book, which is highly entangled, the information isn't written on the individual pages. It's encoded almost entirely in the correlations among the pages. If you want to read the book, you have to make a collective observation on many pages at once. That's quantum entanglement. And it's very different from any notion of correlation that we normally encounter. And what's really interesting is that these correlations are extremely complex. So that if I wanted to give a complete description using classical language of all the correlations among just a few hundred qubits, I would have to write down more bits than the number of atoms in the visible universe. So it'll never be possible, even in principle, to write that description down. And that feature that it's impossible to express in classical language the correlations among just a few hundred qubits was very intriguing to the physicist Richard Feynman, and it led him to make the suggestion in the 1980s that if we could build a quantum computer which processes qubits and stored a set of ordinary bits, it might be able to perform tasks that are beyond the capability of any conceivable classical computer. What Feynman meant was that if we can't even express in terms of ordinary bits the information content of a few hundred qubits, then perhaps by processing the qubits instead of bits, we'd be able to perform a task that no digital computer would ever be able to emulate. And that vision was partly vindicated some years later by the computer scientist Peter Shor. Shor was studying the problem of finding the prime factors of large composite integers, a problem which we think becomes very hard when the number to be factored is long when we use an ordinary digital computer. But what Shor realized is that for a quantum computer, the factoring problem would be easy, not much harder than multiplying numbers together to find their product. And when I heard about this discovery in 1994, I was really awestruck, because I realized what it meant is that the difference between a hard problem and an easy problem, the difference between problems that we'll never be able to solve even with advanced technologies and problems that we can hope to solve as technology advances, that difference between hard and easy is different than it otherwise would be because we live in a quantum world instead of a classical world. I thought that was one of the most interesting ideas I had ever encountered in my scientific life. And thinking about it eventually led me to change the direction of my own research from elementary particle physics to quantum computing. Now, does anybody care whether factoring is a hard problem or not? Yeah, actually a lot of people care. Because the hardness of factoring and other number theoretic problems is the foundation of the security of the cryptographic protocols that we use routinely to protect our privacy when we communicate over the internet. When quantum computers are widely available, then we won't be able to protect our privacy in that same way. Alternatives exist, but it's still not exactly clear what will be the best way to protect privacy in the coming post-quantum world. The broader lesson that we learned from Shor is that there's a distinction between types of problems. There are problems which are classically hard and quantumly easy. Problems that are hard to solve with classical computers and easy to solve with quantum ones. I think that's one of the deepest things that's ever been said about the difference between quantum and classical. And it becomes a compelling problem to understand better what are these problems that are classically hard and quantumly easy. And we've learned some things about that, but I think there's much more yet to be learned. From the perspective of a physicist, I think what's most significant about quantum computing is that we expect that with a quantum computer, we'd be able to efficiently simulate any process that occurs in nature. And we don't think that's true of ordinary digital computers, which we believe cannot simulate very highly entangled quantum states. So with a quantum computer, we ought to be able to probe more deeply into the properties of complex molecules and exotic materials, and also probe fundamental physics in new ways, for example, by simulating high-energy collisions of elementary particles, or the quantum behavior of a black hole, or the quantum behavior of the very early universe right after the Big Bang. So a lot of effort has been expended over the last 20 or so years in finding applications we can run on quantum computers. One of my friends, Eddie Farhi, has been a leading contributor to that subject, and some years back when he wrote one of his characteristically brilliant papers on the subject of applications for quantum computers, I was moved to send him a poem which began, "We're very sorry, Eddie Farhi, your algorithm's quantum. Can't run it on those mean machines until we've actually got them." And the poem goes on, but you get the idea. Brilliant people have been coming up with great applications we can run on quantum computers, but we can't yet run them because we don't have quantum computers that are powerful enough. Which raises the question, why is that? Why don't we have quantum computers already? And the answer is it's really, really hard to build one. And part of what makes it hard is the phenomenon that we call decoherence. Physicists like to imagine a cat that's both alive and dead at the same time. But we never experience that type of coherent superposition of macroscopically distinguishable objects, and we understand why not. It's because interactions with the environment would in effect immediately measure the cat and project it onto a state which is completely dead or completely alive. That's decoherence. And it helps us to understand why, even though quantum physics holds sway in the microscopic world, nevertheless, classical physics provides a quite adequate description of ordinary experience. Now, a quantum computer won't be otherwise a whole lot like a cat, but it too will inevitably interact with its environment, even though we might try hard to prevent that. And that will cause decoherence, which will mean the delicate superposition state in a quantum computer would be damaged, and that would cause the quantum computation to fail. So we can't expect to build powerful quantum computers that solve hard problems unless we can protect the quantum computer from decoherence and other potential sources of error. Errors can be a problem even in the ordinary classical world. We all have bits that we cherish, but everywhere there are dragons lurking who delight in tampering with our bits and flipping them to another color. But in the classical world, we've learned to defend ourselves against those dragons. If I have a bit that's very valuable that I want to be sure to protect, I can store backup copies of the bit. And then the dragon might come along and change the color of one of the bits. But I can ask a busy beaver to frequently check the balls, and whenever he sees one which is a different color from the other two, he repaints it so that they all three match again. So then if the dragon hasn't had a chance to change the color of two of the balls, the value of the bit is preserved. It's protected because we've encoded it redundantly. And we'd like to use that same principle of protection via redundant encoding for quantum information. But at first there seem to be difficulties because, as I already mentioned, we can't copy unknown quantum states. So I can, for example, make a backup copy of the state of a quantum computer in the middle of a computation in case the original gets damaged. And with quantum information, there are more things that can go wrong than with ordinary classical bits, because it might be that the dragon opens door number 1 and changes the color of the ball and recloses the box. That would be like a bit flip that occurs on classical data. Instead, the dragon might open door number 2 and change the color of the ball and reclose the box. And that's what we call a phase error on the quantum information, which has no classical analog. But we need to be able to protect against both the bit flips and the phase errors. There's another way of thinking about the phase errors. The dragon might open door number 1 on the box and, rather than flip the bit, observe the value of the bit and remember it. And that'll have the effect of flipping the color of the ball, at least with some non-negligible probability, if we look inside the box through door number 2. And because it's often easier in many physical settings for the environment to remember a bit rather than flip a bit, these phase errors are an especially pervasive source of noise in many quantum hardware platforms. So the real problem is that with quantum information, unlike classical information, if you observe a quantum state, you unavoidably disturb it in an uncontrollable way. That's not true of classical information, but it's an intrinsic feature of quantum information. So if we want to process quantum information reliably, we have to keep it almost perfectly isolated from the outside world, from the environment, to prevent the environment from acquiring any information about the state which would disturb it. And that sounds impossible because our hardware is never going to be perfect, but we've understood in principle how to do it using the idea of quantum error correction. If I have a qubit that I want to protect from damage, I can encode it in the form of a highly entangled state of many qubits, let's say 5 qubits, and I can choose that entangled encoding so that if the dragon comes along and manipulates any one of the 5 boxes, the dragon won't be able to acquire any information about the encoded state by looking at that one box. It's just like the 100-page book I described earlier. You can't read the book, in this case, read the encoded quantum information by looking at the pages, in this case, the physical qubits, one at a time. And that means that I can ask the beaver to check the qubits and just verify that they have the right kind of correlations, and if they don't, repair the damage by restoring those correlations. And in doing so, the beaver doesn't have to acquire any information about what the encoded state is, and therefore need not damage it. So it really is possible to redundantly store quantum information so it can be protected from damage if we do it the right way, and the secret is to use quantum entanglement. That is, if I want to protect a quantum state from damage, I should encode it in a highly entangled form among a system with many parts, and then the environment might interact with those parts one at a time, like when we were reading the pages of the 100-page book one at a time, but will not be able to acquire any information about what the encoded state is because it's not written in the individual parts, but only in how they're correlated. And we've also understood how to process reliably information that is encoded in this highly entangled form so we can operate a protected, fault-tolerant quantum computation. So although we might not see an actual cat in a superposition of alive and dead anytime soon, we should in the not very distant future be able to encode a cat in that type of delicate superposition state and maintain it in a quantum memory for as long as we please. Now, we discovered these principles of quantum error correction back in the 1990s, and it was a very exciting time. My student at the time, Daniel Gottesman, was moved to write a quantum error correction sonnet, which read in part, "We cannot clone perforce, instead we split coherence to protect it from that wrong that would destroy our valued quantum bit and make our computation take too long." And the sonnet goes on because it's a sonnet, but you get the idea. We were very excited. It's a very pretty idea, but that was over 20 years ago, and we're just now getting to the stage where the technology is sufficiently advanced that we can use these ideas of quantum error correction in the laboratory and explore how well they work. Another hero of our story is my Caltech colleague, Alexei Kitaev. When we first met on his first visit to Caltech in 1997, that was one of the most exciting days of my scientific life because as I listened to Kitaev's seminar and made these notes, I realized that I was hearing from him ideas about quantum error correction that are potentially transformative. What Kitaev taught me was the connection between quantum error correction and topology. Topology is the word mathematicians use for properties of an object which remain invariant if we deform the object without breaking or tearing it. And one physicist who was perhaps the earliest to appreciate the deep connections between physics and topology was David Finkelstein. When it comes to quantum error correction, well, what we would like is the way a quantum computation acts on protected quantum information to remain invariant when we deform the computation by adding some noise. And so we would like to make use of physical interactions that have a topological character. And physicists know of such interactions. We know, for example, that if a charged particle like an electron is transported around a tube of magnetic flux, its quantum state changes in a way which depends on the amount of magnetic flux confined inside that tube, even though the electron never directly visits the region where the magnetic field is non-zero. And furthermore, that change in the quantum state is a topological property. It remains invariant if we deform the trajectory of the electron as it winds around the tube. The only thing that matters is the winding number, the number of times that the electron goes around the tube. Now, we can engineer, using semiconductor technology, a kind of two-dimensional world in which electrons live between two slabs of semiconductor. And in a two-dimensional world where particles are very highly entangled, very rich topological interactions can occur. In that two-dimensional world, the particle excitations, which we call anyons, have several nice properties. First of all, if there are many such particles, many anyons, there are a vast number of quantum states which can be realized by stitching the particles together. But every one of those quantum states looks exactly the same if you examine the anyons one at a time. So that's just the kind of encoding of quantum information we would like, to have an intrinsic resistance to decoherence due to interactions with the environment, because the environment interacts with the anyons locally, and if they're kept far apart from one another, and nothing can be revealed about the quantum state when you visit the anyons one at a time, then it will be a well-protected state against decoherence. And furthermore, we can process the information carried by the anyons by performing exchanges of neighboring anyons in which they swap places. And so we can imagine operating, following Kitaev, a topological quantum computer. We'd initialize it by producing pairs of these two-dimensional particles in our two-dimensional world. And then we would process information by performing a sequence of exchanges in which neighboring particles change places, so that the the world lines of the particles, the anyons in 2 + 1 dimensional spacetime, would trace out a braid. And then to read out a result, we could bring the anyons together in pairs and observe whether they annihilate one another and disappear. What's beautiful about this type of computation is that it has an intrinsic resistance to decoherence. As long as we keep the temperature low, so no unwanted thermally produced anyons are diffusing around, and as long as we keep the anyons far apart from one another, except at the very beginning and the very end, so there are no unwanted, uncontrolled interactions between the anyons, then as long as the particles trace out the right braid, we'll get the right answer. So I was very excited by this idea, and so I wrote a poem, which read in part, Alexei exhibits a knack for persuading that someday we'll crunch quantum data by braiding, with quantum states hidden where no one can see, protected from damage through topology. Enyon, enyon, where do you roam? Braid for a while before you go home. And the poem goes on, but you get the idea. It was a very beautiful vision of how a quantum computer might work, kind of a theorist's dream. But can it really be realized in the laboratory? Well, here too, Kitaev had a bold idea, which is we can divide electrons in half. Now that sounds ridiculous because everybody knows an electron is an indivisible elementary particle. But in an entangled world, quite amazing things can happen. So let's consider a superconducting wire. This wire is at very low temperature, so it can conduct electricity with no resistance. But there are two types of superconducting wire, the ordinary type and a more exotic type, which is called a topological superconductor. And if we have a segment of topological superconductor with ordinary superconductor on either side, at the endpoints of the segment there resides an object we call a Majorana mode. And now if you add an extra electron to that segment of topological superconductor, the electron dissolves and disappears. And as it does so, the state of the two Majorana modes on the two ends of the segment changes. But that change is invisible locally if you look at the ends of the segment one at a time. It's really a collective property of the two ends, which are far apart from one another. And that makes the information that an electron has been added hard to detect for the environment. It's very well hidden information. So if I encode a qubit according to whether the number of electrons in that wire segment is an even or an odd number, that qubit is very well protected against decoherence. Or at least that's the idea. And experiments have been done in the last few years to observe whether this type of protected storage of information is really possible in quantum wires. And there is by now persuasive evidence that such topological protection can be achieved experimentally, but the experiments are still not completely conclusive and further experiments will be needed. Of course, we'd like to do more than just robustly store quantum information. We want to be able to process it. And here's how that might be done. We could build a network of wires with T-junctions, and the Majorana mode, which is located at the place where the topological superconductor and ordinary superconductor meet, can be moved around by changing voltages underneath the wire sample. And that means that I can park one of the anyons around the corner, move the one on the right over to the left, and then unpark the first one. And in doing so, the two Majorana modes will have changed places. They behave like anyons, and this would be one step in a protected topological computation in which the anyons are manipulated. That type of experiment hasn't been done yet, but we're hopeful it can be done in the next couple of years. And if that happens, this will not just be a step towards a potentially remarkable new technology, but a real milestone for quantum many-particle physics. Now, I don't want to give the impression that this exotic topological approach to quantum computing is the only type of hardware that's currently being developed for potential quantum computers. That's far from the case. There are a number of other possible hardware platforms. I've already mentioned the possibility of storing information in the polarization state of a single photon. Another possibility is to use as our qubit a single electron which has a magnetic field which can point either up or down, giving two states for the qubit, or a single atom which could be in either its ground state, its lowest energy state, or some very long-lived excited state. So these three are really all very remarkable encodings with the information carried by just a single particle, and yet we can manipulate that information with today's technology quite accurately. There are also more complex encodings that are possible. For example, using a superconducting circuit at very low temperature, not the type of exotic topological superconductor I mentioned a moment ago, but an ordinary superconductor where we can envision the two states of a qubit as a persistent current in a loop of wire which could be oriented either clockwise or counterclockwise. And that's also a quite remarkable encoding because in this case, the qubit is carried by the collective motion of billions of electrons, and yet for information processing purposes, it behaves just like a single atom. So where's the technology now? We are at the brink of what has been called quantum supremacy. That means quantum technology which is capable of performing tasks that surpass what we can do with today's most powerful supercomputers. And it's useful to have a word for this new era of information processing, which is now opening up. So I suggested the word NISQ. It stands for Noisy Intermediate Scale Quantum. Intermediate scale means devices big enough so that we can't, by brute force, simulate what they're doing using ordinary digital computers, at least the ones we currently have. That means a device with 50 qubits or more. But noisy emphasizes that these devices will have rather low quality qubits and they will not be error corrected, so that every time we do a quantum gate acting on a pair of qubits, there's a probability of an error in the gate of about, say, 1 part in 1,000 or worse than that. And so that noise limits how complex a computation we can execute and get the right answer at the end with some reasonable probability. Now, NISC is exciting for physicists. It means that we'll have the opportunity to explore the physics of many entangled particles in a regime which up until now had not been experimentally accessible. And this technology might have interesting applications, perhaps ones which are commercially viable in the near future, but we're not at all sure about that. We shouldn't expect NISC to change the world by itself. It should be regarded as a step towards more powerful quantum technologies we hope to develop in the future. I am confident that quantum technology will eventually have a transformative effect on human society, but we don't know how long that's going to take. There's an emerging paradigm for how these near-term NISC devices might be used in applications, a kind of hybrid quantum classical strategy. It makes sense to use our existing digital computers to the extent that we can and then boost their power, if possible, using a quantum coprocessor. And the way that might work is we would do a relatively simple quantum computation and then measure all the qubits and then feed the outcomes of those measurements to a classical computer, which would return instructions to slightly modify the quantum computation, and then that cycle would be repeated with the goal of finding an approximate solution to some very hard optimization problem. Now, should we expect that NISC devices in the near future running this type of classical quantum hybrid scheme, will they be capable of solving problems which are too hard with other existing technologies? Well, we don't really know. We're going to try it and see how well it works. But it's a lot to ask, because the classical methods are well honed after decades of development, and these NISC processors are just becoming available now for the first time. So we're going to have to experiment with them, understand their capabilities, and as we experiment, learn new applications and how to make good use of them. Now, as I've emphasized, these NISC-era devices will not have error correction, and that will put a limit on their computational power. In the long run, quantum error correction will be the solution to that problem of noise, and it will allow us to build powerful, large-scale quantum computers that can solve very hard problems. But quantum error correction has a high overhead cost in terms of the number of physical qubits and gates that we need. And how high that cost is depends on the quality of our hardware, how likely it is to make an error, and on the problem we're trying to solve, the complexity of the algorithm that we run. But for example, if I were trying to solve a chemistry problem, which seems to be beyond the state of the art of what we can solve with existing digital computers on a quantum device, using hardware with a quality comparable to what we currently have, then I would probably need hundreds of protected qubits and altogether millions of physical qubits to get that computation to work. Whereas we're likely to have only devices with hundreds of physical qubits in the next few years. So we're going to have to cross a daunting quantum chasm from where the technology is going to be in the next few years to where we eventually want to go to have truly scalable quantum computing. And that's going to take a while. But it's important in the meantime to continue to advance the technology to realize better qubits, better gates, better systems engineering, better design of algorithms and error correction ideas, all of which will bring us closer to the era where error-corrected, fault-tolerant quantum computers can solve really hard problems. So I've been talking mostly about 3 questions about quantum computers. Why would we want to build one? Well, the best answer we have to that is that we think a quantum computer will be able to simulate efficiently any process that occurs in nature. Can we really build one? Well, now that we understand the principles of quantum error correction, we are not aware of any obstacle that will prevent us from succeeding. And how will we do it? Well, as I've mentioned, there are a number of different approaches to building the hardware of a quantum computer, which are now under development. And it's important to follow those different approaches in parallel, because nobody really knows at present what technology is going to turn out to be the one with the best prospects for scalability to large devices. Now, these three questions, I think, make for a rather compelling research agenda, and a lot of my own work over the last 20 years has been devoted to these questions. But I'm not an engineer. I'm a theoretical physicist, and what interests me the most are the ways in which our maturing understanding of quantum information science is giving us new insights for attacking some of the hardest problems in fundamental physics. The way I look at quantum information science is that we're still in the early stages of the exploration of a new frontier of the physical sciences, what we might call the complexity frontier or entanglement frontier. This is different from the frontier of short distances that we explore in particle physics, or very long distance, as in cosmology. But like those, it's very fundamental and exciting. We are now acquiring and perfecting the tools for creating and precisely controlling very complex states of many particles, highly entangled states, so complex that we can't simulate them using our most powerful digital computers or describe their properties very well using existing theoretical tools. And that's opening opportunities for new discoveries. One noteworthy trend is that there's been a surge of interest in quantum information and quantum computing ideas in recent years among the scientists who work on problems in elementary particle physics and gravitational physics. These people have been struggling for years to understand some very hard problems, such as what is the quantum behavior of a black hole? And that struggle has given rise to a very remarkable idea that we call the holographic principle. An idea which, by the way, was to a degree anticipated by David Finkelstein. The holographic principle asserts that, contrary to naive appearances, all the information in a room like this one, in our brains and our cell phones and so on, is actually encoded, but in a very, very scrambled form, which is exceedingly hard to read, on the boundary of the room, the floor and the walls and the ceiling. And what we're starting to appreciate is that information about the geometry in the room, about who in the auditorium is sitting next to who else, that geometrical information is encoded in the structure of the quantum entanglement of this very scrambled boundary description. So really, in a sense, it is quantum entanglement that is holding space together. At a recent Caltech event, Robert Digraph, the director of the Institute for Advanced Study at Princeton, gave a talk. And at the end, he showed this slide indicating how the ideas of theoretical physics are related to one another. And I was struck by the way Digraph put quantum information right at the center of things. He probably wouldn't have done that a few years earlier. This idea that quantum information is a unifying principle of physics is just starting to get traction in the last few years. But where I would deviate from Digraph is I would cross out the word theoretical, because quantum information is an experimental subject. And if it's true, as we increasingly have reason to believe, that the geometry of space is really an emergent property associated with quantum entanglement in a deeper description of reality, then it can be imagined that deep insights into the quantum structure of space-time will arise from laboratory experiments studying highly entangled quantum systems. On a tabletop in a laboratory at a place like Georgia Tech, we ought to be able, by creating and studying very highly entangled quantum systems, to, in effect, create spacetimes that didn't exist before and study their properties. I hope that's a bold enough idea for you. And even if that prophecy does not come true, I think we can say with high confidence that many rousing surprises await us as we explore the entanglement frontier. Thanks a lot for listening to me.
So we'll now take any questions. So just please raise your hand and I'll try to come and find you with a working microphone.
Do you think Wheeler's in his It's for Bits paper that his assertion that there's no continuum is true?
So the question makes reference to ideas of John Wheeler, another visionary physicist, who used the slogan "it from bit" to try to understand or express the mystery of how the quantum world arises. And then you ask, do I think it's true that the world is really discrete and that a continuum does not exist? Well, it depends exactly what you mean by that. I think it would probably be uncontroversial to say that it doesn't make sense to speak of space on distance scales which are arbitrarily short, or time on time scales which are arbitrarily short. And one way of thinking about what goes wrong if you try to probe physics at shorter and shorter distances is that any such probe will create a black hole. In fact, the way particle physicists usually explore physics at shorter and shorter distances is they collide particles at increasingly high energy. And that allows you to resolve structure at finer and finer scales. But eventually you have so much energy that the particle collision creates a black hole, and then when the energy gets higher and higher, you just make a bigger black hole, and it doesn't allow you to probe with better resolution. So there's a fundamental cutoff on distances which really makes sense, what we call the Planck scale. It's about 10 to the minus 35 meters. So at least in that sense, I would agree that there is no space-time continuum.
More questions?
Yeah, I'm not a physicist, but I did study physics at with David Finkelstein for about 10 years on weekends at the University of Starbucks. He was an amazing person. His widow, his wife, is here today. He contributed greatly to the civil rights movement back in, where was it, Tupelo, Mississippi, Flamit? Where'd you go?
Tugalo, Mississippi.
Yeah, Tugalo, Mississippi, excuse me. But I just wanted to point that out. But my question is, in the 90s, Peter Shor stated that once quantum computing was developed, the de-encryption of any information was possible. So my question is, doesn't that make it so urgent? Because in today's global competition, the country that gets it first, which hopefully will not be Russia or North Korea, puts us in great danger.
So I think the question is about the vulnerability of encryption to attack by quantum computers and how urgent a matter is that. It's a good question. So you might say that maybe we don't have to be worrying about that right now. Quantum computers that can run Shor's algorithm and factor large numbers and break the crypto systems that we're using now may be some years away. But actually, we should be worrying about it now because there are several timescales we ought to have in mind. First of all, if we're going to replace the public key crypto systems that we're using now with new standards, it takes a lot of time to put those new standards into place. And in addition, whenever we use a secret key for encrypted communication, well, we would like our privacy to be protected for some time after the use of the key. So if you want a private conversation that you're having today to remain secret, say, for another 20 years, and if you think that it's going to take, say, 15 years to put new public key crypto system standards into place, then you really got a problem if people are going to have quantum computers running Shor's algorithm in 35 years. And nobody can promise you that that's not the case. So what are we going to do? There are two paths to follow. One of them we call post-quantum cryptography. And what that means is replacing the crypto systems that we're using now, which can be attacked by quantum computers effectively, by new crypto systems which we believe are hard to attack even with quantum computers. But we can't prove the security of those proposed new protocols, so we would have to rely on computational assumptions about the hardness of the problems on which those new systems are based. The alternative approach is what we call quantum cryptography or quantum key distribution, and that would require that we replace the existing classical communication infrastructure by a new quantum internet, which would allow us to send qubits, presumably photons, which are the best traveling qubits, from station to station. And the nice thing about that is we wouldn't have to rely on computational assumptions. We can show that the security follows just from principles of physics. My guess is that both of these methods will be used, that depending on the needs of the users, some will prefer the option of post-quantum crypto, some will prefer quantum key distribution. But there's a lot of work to do to bring either one of those technologies to the level where it's ready for deployment. So I do consider it to be an urgent problem.
Hey, thank you so much for your talk. Appreciate it. So given the current landscape of experimental quantum computation that's going on right now, are there any hard skills, like lab skills, programming skills, that you would recommend that people sort of focus on to develop in the next coming years to make themselves, I guess, useful to the future of quantum computing research?
So I think the question is, what kind of training is required or advisable for a young scientist or engineer who is interested in participating in the quantum technology industry? And in particular, whether different languages or computing methods should be part of that training. It's a good question. Actually, there are a lot of quantum technology companies which have either started up or have significantly ramped up their investment in the last couple of years. And some of them complain that it's hard to find people with the right kind of training. Because it's a very interdisciplinary field, you need teams of people who have some understanding of quantum physics, understand the engineering challenges, and also know something about the physics of the hardware. And there are very few people now who have training which gives them a solid background in all of those things. So I would rather not answer the question by saying there's a specific thing that you need to know, but I think the people who will be valuable to these technology companies are those with the willingness and the background to communicate effectively with people out of their areas of expertise. I think, you build a team, you need a microwave engineer, and that person had better be an expert on microwave engineering and doesn't necessarily have to be the world's leading expert on quantum algorithms. But having the engineers able to talk to the computer scientists and talk to the physicists is very valuable. So if you can acquire a broad enough background so you are comfortable communicating across those boundaries, I think that will make you better prepared for a career in the quantum industry.
Anybody else with a question? We probably have time for a few more. Just show me your hand so I can get you afterward.
Hello. I just want to thank you for your talk. I believe your analogies and poetry did an excellent job of bringing quantum concepts down to like a more intuitive approach for a first-year CS major like me. So you mentioned that in the near or far future that quantum computing will become more ubiquitous. So right now in our school system, we study more of a classical architecture of the computers and the bit approach. Do you feel that as quantum becomes more relevant and ubiquitous that it will eventually supplant and replace the study of classical architecture?
So the question was, as quantum computing technology advances, will classical computing architectures become obsolete? I doubt it. I mean, nobody really knows. But the way we see it now is that quantum computers will have specialized applications. They'll probably be accessed by most users through the cloud. And most of the things that you do on your computer today, which you'll still want to do, you will continue to do with classical computers. Maybe I'm not being visionary enough or thinking long-term enough. Maybe David Finkelstein would say, well, of course it'll all be quantum computing in 300 years. But I would say within our lifetimes, classical architecture will not become obsolete. And you're much younger than I am.
If there's any more questions?
Hello. Can you comment? It's my understanding there's some teleporting experiments that are being done in Spain using entanglement at the atomic level. Can you comment on that? And I'm just curious about what's going on there.
I didn't see the person who asked the question. You're way back there? Oh, okay. Hi. Now, the question was about quantum teleportation. Yeah, quantum teleportation is a very useful primitive in quantum protocols. What is it? It's a way of sending quantum information from one location to another, making use of shared quantum entanglement between the two locations and classical communication from one location to the other. And because we use the classical communication, maybe it doesn't seem so remarkable that we can send a quantum state from Pasadena to Atlanta using quantum entanglement as well as classical communication. But it actually is rather remarkable. One way of thinking about it is that it's a very highly encrypted form of communication. So if you and I share entanglement, I have half of the entangled state at Caltech, and you have the other half at Georgia Tech. And then I have a quantum state that arrived in my lab today. Then I can perform a measurement on the newly arrived quantum state in my half of the entangled state, and then send my measurement outcome to you, and you can interpret my measurement outcome as an operation that you have to perform on your half of the entangled state to recreate the state that had arrived in my lab today. But in fact, the classical bits that I send to you are just uniformly random. They don't convey any information by themselves about what the quantum state is. So it's really the entanglement together with the classical communication that does the job. Notice that classical communication was required. I'd have to call you up on the phone or something to tell you the outcome of my measurement. So it's not that we instantaneously convey the quantum state from Pasadena to Georgia Tech. The information can't be recreated in your lab in Georgia Tech until you receive my phone call. So there's a common misconception that teleportation means that we can send quantum states faster than light. No, that's not it. But it's still a very remarkable protocol because it has that highly encrypted structure that I explained.
All right, any last questions? I think we have time for maybe one more.
Hello. You talked about how we could have like 50 to 100 qubit computers soon. I was wondering, like, kind of experimentally and physically, what have we been able to build so far, or where the experiments are at?
Yeah, okay. Well, I have a slide. Maybe I should show it. I didn't removed it from the talk. So here's just to give you an idea of where things stand. Among the industry players are IBM and Google, which are working on superconducting technology for quantum computing. IBM has announced construction of a 50-qubit device, and Google a 72-qubit device, but so far we have not seen experimental data from either one of those devices. So we don't know exactly what their status is. IBM has a cloud interface to a 16-qubit quantum computer, which you can use yourself, what they call the IBM Quantum Experience, and it's in fact been widely used. Some of the other companies are either have or will soon have such cloud interfaces, including Rigetti. Rigetti also uses superconducting quantum circuits. They've announced that they're building a 128-qubit processor. However, not that that construction has been completed, and I don't know that they've announced a date by which they expect it to be available. There's also a commercial company called IonQ that is using atoms as qubits, trapped ions, and they are building a 32-qubit processor, or at least have announced that they're doing so, but not that it has been completed. Now, meanwhile, there are what we call quantum simulators, which are not general-purpose quantum computers capable of doing any quantum computation, but nevertheless have quite interesting applications for studying highly entangled matter, and those are becoming increasingly controllable. So, for example, there were recent experiments using 51 neutral atoms and another using 53 trapped ions for studying the complex dynamics of many qubits. And meanwhile, there are quite a few other experimental platforms which are continuing to be developed, but are not quite at the stage of the ion trap and superconducting circuits that I mentioned. Let me emphasize again that one hears a lot about the number of qubits, and it is very important, but it's not the only thing that matters. Also very important is the quality of the qubits. If I have many qubits, but the gates that I can do have very poor fidelity, that would not be a very useful quantum computer. So it's really a combination of high gate fidelity and many qubits that we need to have potentially interesting applications.
All right, so those of us who work in quantum know that when someone asks about gate fidelities, that we should probably just wrap it up. So let's take one chance here to give John Preskill a big thank you.